Hey everyone, welcome back to our course on patient care and safety in sonography. In this lesson, we will discuss mechanisms of bioeffects, including thermal and mechanical effects, and their potential impact on biological tissues. Understanding these indices is crucial for minimizing patient exposure and ensuring the safe application of ultrasound imaging in clinical practice. Let's get started. Ultrasound imaging is widely regarded as a safe and non-invasive diagnostic tool. However, like any medical imaging modality, it carries some risks, particularly concerning bioeffects. Bioeffects in ultrasound result from sound waves interacting with biological tissues, primarily through thermal and mechanical mechanisms. Understanding these effects is essential for optimizing image quality while ensuring patient safety. First, let's discuss thermal bioeffects. Thermal bioeffects occur when ultrasound energy is absorbed by tissue and converted into heat. This process is influenced by acoustic intensity, frequency, exposure time, and tissue type. Higher intensity ultrasound waves produce more heat because they deliver greater acoustic energy to tissues, which is then absorbed and converted into thermal energy. Higher frequency waves, while less penetrating, are absorbed more efficiently by tissue, leading to localized heating. This occurs because as ultrasound waves travel through tissue, their mechanical energy is absorbed by molecules within the living tissue, causing them to vibrate and generate heat. Longer exposure increases the likelihood of significant temperature rises. Certain tissue types, such as bone, absorb ultrasound more efficiently than soft tissues due to their higher density and composition. This absorption can create localized heating near bones, which is particularly concerning in fetal imaging. Prolonged or excessive heating can lead to tissue damage, especially in sensitive structures such as the developing fetal brain. Next, let's discuss mechanical bioeffects. Mechanical bioeffects result from the physical interaction between ultrasound waves and tissue structures. The primary mechanical effect of concern is cavitation, which occurs when gas bubbles created by sound waves within tissues expand and collapse due to variations in acoustic pressure. Cavitation can be classified into two types: stable and transient. Stable cavitation involves small gas bubbles oscillating in response to pressure fluctuations without collapsing, which can cause microstreaming, which is the small-scale movement of fluid around oscillating gas bubbles in response to an ultrasound wave and lead to subtle mechanical stress on cells. The oscillating bubbles can open transient pores in the cell membrane, which may let molecules in, but this effect is reversible, allowing the cell to survive. Stable cavitation is generally considered a low-risk effect, but can be problematic with prolonged exposure, leading to cell membrane disruption. Transient cavitation occurs when gas bubbles rapidly or violently expand and collapse, generating high local temperatures and pressure that may damage surrounding tissues. Cavitation effects are more likely to occur in tissues containing gas, such as the lungs and intestines, and in applications utilizing high-pressure ultrasound pulses, such as contrast-enhanced ultrasound imaging. Next, let's discuss the thermal index. The thermal index, or TI, is a unitless measurement used to estimate the potential for tissue heating during ultrasound imaging. It represents the ratio of the acoustic power used to the power required to raise tissue temperature by 1 degree Celsius. There are 3 variations of TI, each relevant to different anatomical considerations: soft tissue TI, TIS, bone TI, TIB, and cranial TI, TIC. The TI value is influenced by power output, exposure duration, and tissue composition. A higher power output increases the TI. Increasing exposure duration, that is, using longer scan times, allows for more time for heat accumulation. Areas with high absorption properties, such as bone, exhibit greater temperature rise. Clinicians must monitor TI values, which are displayed on the ultrasound system monitor. TI values are particularly important in obstetric imaging, where fetal tissues may be more susceptible to heat-related damage. Regulatory guidelines suggest keeping TI values below 1.0 for fetal scanning and minimizing exposure duration. Finally, let's discuss the mechanical index. The mechanical index, or MI, quantifies the likelihood of cavitation occurring in biological tissues. It is defined as the peak negative pressure divided by the square root of the ultrasound frequency. The peak negative pressure represents the highest rarefactional pressure in the sound wave, while the ultrasound frequency is measured in megahertz. A higher MI indicates a greater potential for cavitation. To minimize risk, clinicians adjust MI settings based on tissue type, ultrasound mode, and patient population. Gas-containing tissues are more susceptible to cavitation. Doppler and contrast-enhanced imaging may require lower MI values to prevent microbubble disruption because these imaging modalities rely on the stability of gas-filled microbubbles for accurate imaging. It is important to note that the risk of cavitation is higher in developing fetal tissues and should be carefully monitored. Both the TI and MI provide real-time feedback, which is visible on the ultrasound monitor, to sonographers and physicians regarding potential bioeffects. Clinical best practices aim to maintain these indices at the lowest settings necessary to achieve diagnostic quality images. Strategies for minimizing bioeffect risks are informed by adhering to the ALARA, or as low as reasonably achievable principle, to ensure ultrasound exposure is minimized while maintaining sufficient diagnostic information. These strategies include reducing scan time, particularly in fetal and pediatric imaging, using lower output power settings when feasible, and understanding tissue-specific risks, such as higher thermal absorption in bone and increased cavitation likelihood in gas-containing structures. Let's take a moment to check our understanding. Which of the following best describes the significance of the thermal index, or TI, in ultrasound imaging? A. It measures the likelihood of cavitation in biological tissues. B. It quantifies the peak negative pressure of an ultrasound wave. C. It represents the potential for tissue heating due to ultrasound absorption. D. It calculates the energy reflected from different tissue interfaces. The correct answer is C. It represents the potential for tissue heating due to ultrasound absorption. It provides a ratio of the acoustic power used to the power required to raise tissue temperature by 1 degree Celsius. The TI is critical in fetal imaging, where excessive heating can cause developmental concerns. The mechanical index, or MI, rather than TI, quantifies the likelihood of cavitation. The TI does not measure peak negative pressure or reflected energy. In summary, bioeffects in ultrasound imaging arise from thermal and mechanical interactions between sound waves and biological tissues. The TI provides a measure of potential tissue heating, while the MI quantifies cavitation risks. By understanding and monitoring these indices, clinicians can optimize patient safety while ensuring effective diagnostic imaging. Continuous advancement in ultrasound technology and adherence to safety guidelines further contribute to the safe application of diagnostic ultrasound.